everybody to Calculus via video. So hopefully you're able to get this work. This is going to be a very fast video, so you're going to have to pause and rewind, but I have a lot of stuff to teach you in 15 minutes. Here are guidelines as outlined in your book on how we can use what we've learned with differentiation and implicit differentiation and the chain rule to help us solve real-world problems. The first step you're always going to do is identify all the given quantities and what you are looking for. Make a sketch of what's happening and try to label everything. Then, write an equation that involves all the things that you know and don't know. Using the chain rule, you'll implicitly differentiate the different terms of the equation from part 2 and with respect to time t. And it's usually going to be with respect to time. After completing step 3, substitute in the resulting equation with all the known quantities and then solve for what you need. Here is an example. A ladder that is 13 feet long is leaning against the wall of a house here. The base of the ladder is sliding away from the wall at a rate of 1.5 feet per second. How fast is the top of the ladder moving down the wall when the top of the ladder is 5 feet from the ground? Here's the key sentence right there. In fact, I'll highlight it. That's going to tell us what our goal is. We want to know how fast is the top of the ladder moving down the wall when the top of the ladder is 5 feet from the ground. So what's going to happen here is you have this ladder, right? And so I'll kind of sketch a ladder here, and it's from the looking at the side of the ladder. So it's just going to look like kind of a line here, but you imagine there's a ladder, right? And you know that the top of the ladder is 5 feet from the ground, so I'm going to label that as 5 feet right there. And then the base ladder is going to be some unknown distance x. We know that the ladder itself is always 13 feet. Okay? We know that the base of the ladder is sliding away from the house at a rate of 1.5 feet per second. 1.5 feet per second. So what is that here? You see feet per second. That should be a hint to you. Feet per second, that's a rate. A rate is usually a derivative. And what is it? What's changing? What quantity is changing? The x. So we would call that dx with respect to time, dt. dx dt is equal to 1.5 feet per second. So that's the situation that's happening. What I want to know is how fast is this top of the ladder going downward? Okay, how fast it's sliding downward? Well, this is called our y typically. I want to know how fast the y is changing. So I want to know the dy with respect to time t. That's what I'm looking for. So far, I've done step 1, identified all the given quantities and the ones to be determined, and I labeled them. And I made a sketch, and so I have to write an equation now. So equation that relates this picture, and I'll give you a hint there, it's a right triangle. So I know that 5 squared plus x squared has to equal 13, always. Now I should be careful here. The height is not always 5. Okay, and just at one moment it's going to be 5. So really I should have maybe labeled this y. But eventually I'm going to plug in a 5 there. But this is the equation that relates all 3 of these quantities together. And I should square that 13. Apologize for all of you yelling at the screen right now. So if I square all these things, I should get the Pythagorean theorem. Now what I need to do is step 3, using the chain rule, I'll implicitly derive everything. So if I take the derivative of y with respect to t, I get 2y dy dt, plus then I get 2x dx dt, and that should be equal to 169. Now I'll plug in all the known quantities. So in this case, I know what y is going to be. I want when the height is 5. So I want when 5 is here. So that's why I plugged in 5 there. dy dt I do not know, so I'm going to leave that as dy dt, plus 2 times my x value. Well, to find the x value, I'm going to have to use that special right triangle. And I know that it's at time 5 and 13. This happens to be a perfect right triangle. 5 squared plus 8 squared should equal 13 squared. Let's double check. 25 plus, oops, not 8. It should be 12. My mistake. 144 equal 169. That's true. So yet my x value at that particular moment when the height is 5, it's just supposed to be 12, so put 12 in there. dx dt, okay, that's 1.5 sliding away, and that should all equal 169. Now it becomes a solving problem. So I'm going to do the algebra off screen. Provided I didn't make any calculation errors, this should be what you see. Now, if you need to pause the video and check, you can do that. but that is what you should get after you're done. The top of the ladder is speeding down at 13.3 feet per second. All right, now let's say I'm inflating a spherical balloon at the rate of 7 centimeters cubed per second. How fast is the radius? Now here's the key question. How fast is this radius increasing when the balloon is 8 centimeters wide? Let's draw a picture first. Okay, so here's a sphere, and again, you have to use your imagination. It's hard to draw three-dimensional things on a two-dimensional spot here. Now we have this radius. I'm going to label that with a red radius here. Okay, now we're inflating a spherical balloon at a rate of 7 centimeters cubed per second. So that's the rate of volume. So actually that is dV related to time is equal to 7 centimeters cubed, that's volume per second. So that's the rate at which the volume is changing. I want to know how fast is its radius changing, dr with respect to dt. Now I'm on step 2. I need to, and actually I forgot to label the radius here, it's going to be at 8 centimeters. Now what I need to do is write the equation. It's a step 2 now. Is write the equation that relates all these quantities together. So you'll see that volume of a sphere is equal to 4/3 times pi r to the third power. And now I need to use the chain rule, step 3. Step 3 is the chain rule differentiating it. dV with respect to time, t, is equal to 4/3 pi r cubed. So to differentiate, I'm going to use the power rule and make it 4 pi. And again, that's just a constant pi. So 4 times pi, then r to the second, dr dt. You should recognize this as surface area. That's a really interesting part. The derivative of volume is surface area, or something close to it. Now I'll plug in what I know. This is step 3, so I'm plugging what I know, do the algebra. Again, I have to pause the video just for brevity's sake, but you plug in what we already know. And I'm trying to solve, remember, for dr dt. So I'm going to pause, draw everything in, and you'll see the answer in just a moment. Providing that I made no errors here, you can see that the dr dt is 7/32 pi. And what would the units be? This is centimeters per what? Second. Okay, and then that would be the answer. You don't have to use an approximation on the AP exam. It's perfectly acceptable just to leave it as 7 divided by 32 pi. And I plugged in 8 here because that's what the radius was. Oh, shoot, I already realized an error. What should it be? It should be 64 here. 64 times 4. I apologize for that. Of course, I have to make a mistake right now in the middle of the live video. That's wonderful. 4 times 64 is 256. This becomes 256 pi. Okay, so let's keep on moving then. Water is pumped into an inverted conical tank at the rate of 1 meters cubed per second. There's that meters cubed again. You should notice that that's volume, so this is going to be dV dt. We're going to need that later. The tank is 30 meters high. Okay, it's going to be 30 meters high and 10 meters wide. That means half of 10 is 5. That means that this is what the tank is going to look like. It's not to scale, obviously. Imagine it's a cone as a circular base. How fast is the water level rising when the water is 4 meters deep? Okay, so let's identify all the quantities we know. We know that dV with respect to time is going to be 1 meters, so it's being pumped in. So it's going to be positive 1 meters cubed per second. So it's going to come in. This water is being pumped in this tank, coming in the top like this. Okay, we know that the top of this is 30 meters high. We know that the radius is 5 meters wide. Now I want to know what the height is changing at. What rate is the height changing? How fast is the water level changing? Remember, water level is just the surface of the water. How fast is the water level changing with respect to time? That's my big question here that I want to figure out. Well, the equation that I'm going to have that relates all of it is going to be the volume equation. If you don't remember the volume of a cone, this is in the front of your book on the back of that first page, and it's pi r squared times the height. Now in this problem, we have dV and dH. Those are the only two differential quantities that we concern ourselves with, but you notice we have this problem. We have another variable, r. So if this happens, if you have several variables in an equation, you need to find a way to change your equation to just have two variables, preferably the ones for which you have rates for. Now if you had dr dt, we'd be fine, because then you could just use the product rule. But we don't have dr dt. We don't know how fast the radius is changing. So we need to find a relationship between the height and the radius. Well, if you took this out and made it a right triangle here, the nice thing about a right triangle is that it's proportional. That means that no matter how high this gets, there's always going to be the same ratio between the radius and the long side. It's 30 and 5. And so the similar right triangle, this is the radius, and then this is the height that I chose. Now notice the height would be this thick distance here, the radius would be that thick distance, and then 30 would be the whole thing, and 5 would be the whole thing down there. We know that from right triangles that height over the whole entire height, h over 30, is equal to r over 5. So to solve for r and make a substitution, I'll obviously have to multiply by 5 and simplify. The h over 6 would be r. And this substitution will help make my volume equation friendly to the differentials I have when I use the chain rule. So I'm going to use a substitution here, pi thirds. This is going to become h over 6. I'll have to square that with that substitution, and h. So that means my equation volume becomes pi thirds times h to the third over 6. Again, I squared 36, excuse me. I squared that thing there and multiplied by h again, which ends up being pi over, which is like 36 times 3 would be 108, h to the third power. And that's much more friendly to differentiate, so I can just go ahead and take the derivative of both sides. I'll have dv dt. This is step 3 now, and step 4 is what I'm going to do. So then this constant pi third, it's just going to multiply by 3, so I have 3 pi over 108, which will simplify again to 1 over 36. H squared dh dt, with the chain there. So then dv dt was that 1 meters cubed per second. This is going to be pi over 36. And the h, I know, the h is when I want when the water is 4 meters deep. Excuse me, I had to find it real quick there. 4 meters deep. So I'm going to plug in 4 to my equation. It's going to be 4 squared. And I want to solve for dh dt. That's what I'm looking for. So now I'm going to pause and do the algebra. And you can see now that I plugged in the 4 there, I squared it, I got 16, multiplied by that fraction, it'd be 16 over 1, so I get 16 pi over 36 times dh dt. I have to divide. When I divide 1 by a fraction, you basically will multiply by its reciprocal, so it's actually 1 times the reciprocal of that fraction, which is this thing turned upside down. And then I can reduce that fraction to make it 9 over 4 pi, and again, this is height per time, so it'd be meters per second. So the height, or the water level, is changing at 9 over 4 pi meters per second at that exact moment when the height is 4. Now an airplane is flying at an elevation of 6 miles on a flight on a path that will take it directly over a radar tracking station. Let S represent the distance in miles between the radar station and the plane. If S is decreasing at a rate of 400 miles per hour and S is 10 miles, what is the velocity of the plane? Okay, so here's the plane. Okay, so not a great drawing, don't have a lot of time. So it's flying at a constant altitude, and that altitude is going to be 6 miles above the ground. Okay, there's a radar station just over yonder here, and there's a big old R radar station. Okay, so there is a radar station. Now S represents the distance in miles between the radar station and the plane. The shortest distance from any object is a straight line, so that's S right here. Now, between the radar station and the plane, if S is decreasing at a rate of 400 miles per hour. So remember that's ds, dt is decreasing, so it'd be negative 400 miles per hour. So S is measured in miles, t is measured in hours, so 1 hour. Okay. What I want to know in this problem is what is the velocity of the plane? Well, what is velocity? That's the distance that is the difference in position with time. Now the only position that's changing here is the x position, because I'm keeping that fixed 6 as your height here. So then I want to find a dx dt. Of course, it's just another right triangle problem. The relationship between all of them is that x squared plus y squared will have to equal s squared. Okay? Now in this case we have to do a substitution because we don't know, actually dy dt was going to be 0. We know that the change in y over time is going to be 0 because it's constant. So I can use implicit differentiation now and just go ahead and take the chain rule here, 2x dx dt, then you have plus 2y dy dt, oh, screw that up there, equals 2s ds dt. And now I'm just going to plug in everything I know, and lucky for us we have almost everything. The only thing that we don't know, well, we do know x, well, we don't know x, we know that s is 10, so if you use the Pythagorean theorem here, I have a special right triangle. I don't have a lot of time here, I have about 30 seconds, so I'm going to pause and use video magic here to show you what the answer is going to be.
We're back. Just make sure you guys understand I got the 10 from plugging it in with the s, the 6, so that's a special right triangle. That gave us 8. plugged in all the numbers, and we led to negative 500 miles per hour. Thank you, and goodbye. Stay classy.